Hello and welcome back to your Chem 4 lecture. We are moving on into chapter 12 today on alcohols, phenols, thiols, ethers, and I believe aldehydes and ketones. So we're settling into the organic chemistry portion of the course. And in this portion, you'll see we'll kind of cycle through the same sorts of things, just with different types of compounds. And each chapter will focus on a different class of compounds, or in this case, as you can see, classes of compounds, what those functional groups are, how we name the compounds that contain those functional groups, and then what kind of reactions those functional groups go through. And along the way, we'll talk about some properties of these compounds that make them important in biological or just in everyday life situations. So starting with these four, we're just going to go ahead and define what they are here at the beginning. So first off, alcohol. Of course, you've heard this word before. An alcohol in particular contains what's called a hydroxyl group, which is just an OH. So it's an oxygen that's bonded to a carbon, whatever carbon on your chain is, and then that oxygen has a hydrogen. And these compounds are very important because the presence of this OH group allows the compounds to hydrogen bond. If they can hydrogen bond, then they can interact with water and other biomolecules, and that's what we see. So we'll talk more in depth here in a little bit. Now, a phenol is a special type of alcohol that has a benzene ring with an alcohol group on it. So with the hydroxyl group on it. So it looks exactly like this. This is phenol itself, where it's just a benzene ring with an OH group. A thiol is slightly different. A thiol, rather than having an oxygen bonded to a hydrogen, has a sulfur bonded to a hydrogen. So if you take a look at your periodic table, you'll see that sulfur is directly below oxygen in group 6A. And as we've said, many times before, elements that are in the same group on the periodic table have similar chemical properties. And that's the case here with thiols being analogous to alcohols because sulfur has a similar set of properties to oxygen. And then finally, ethers. Ethers fit into this category a little awkwardly, but it's important that we talk about them. Ethers, rather than having an oxygen that's bonded to a hydrogen, instead, this oxygen is bonded to two carbons. So it basically fits into the main chain of the carbon-containing compound and just kind of splits it up into two halves. So, okay, let's go ahead and take a look at each of these in ball and stick, and then the line angle formulas as well. So remember the line angle formula, we're going to write out all of the non-carbon atoms and the hydrogens that aren't bonded to carbon. So whereas we don't worry about any of the hydrogens that are bonded to the carbon over here, the CH3, because this hydrogen is bonded to oxygen, we do need to write it out. So this is what methanol would look like. And we'll get some practice with this, so don't worry too much yet. Phenol, again, it's just a benzene ring with an OH group on it. Thiol looks like this. Once again, we write out the H that's bonded to the sulfur. And then finally, an ether looks like this. Again, it's just an oxygen takes the place, basically is in the middle of the carbon-carbon bonds. Okay, so we're going to start with alcohols since they're probably the most important of this class of compound. So when we name alcohols, the good news is with the IUPAC system, we're going to keep building off of the nomenclature that we already know. So if you feel comfortable naming alkanes, alkenes, and alkynes, we're just going to build on that with all of these naming systems that we're going to come up with. So yeah, so it should be totally fine. Now, for example, with alcohols, what you do is you basically use the same IUPAC system to name the alkane, but you replace the E that comes at the end of it with OL. We'll point out here that there are common names, which is just the name of the alkyl group followed by alcohol. So like methyl alcohol, but we're not going to use those. We're going to just use the IUPAC names. But I want to mention at least methyl alcohol, ethyl alcohol, and isopropyl alcohol, because these three you will run into in everyday life. Sometimes it's called that. Okay, so if you have a one carbon alkane, it's methane, right? If you have a one carbon alkane that's bonded to an OH group, that becomes methanol. So drop the E, add OL. How about ethane? Ethane becomes ethanol. And again, that would be called ethyl alcohol with the common nomenclature. So let's go ahead and do an example here, and we'll walk through some of the tricky parts of naming this type of compound. So let's walk it through. We're going to look at this compound, and we're going to try to name it as an alcohol. Okay, so step one, what we need to do is identify the functional group, okay? And that's easy enough because we've just learned now that this OH group, that's an alcohol. So we know it's an alcohol, so we're going to name it like an alcohol. Okay, easy enough. So now what we need to do is find the longest chain, and then we're going to name it from there. So the longest carbon chain that is bonded to the alcohol. So we could go 1, 2, 3, 4, 5, 6. You could also start here, 1, 2, 3, 4, 5, 6, or of course go the other way, 1, 2, 3, 4, 5, 6. Either way, any way that you cut it, the longest chain that we have here is 6 carbons long. So we know that would be hexane, right? So hexane is what we start from. But we know that we have an alcohol. So rather than hexane, we're going to put hexanol, like that. Okay, now that's obviously not everything that we need to do, because we have the location of the OH group and the location of this methyl substituent to worry about. So that's what we'll do next. So next up, we should number the carbon chain, right? Well, with alcohols, we are always going to number it so that the hydroxyl substituent is at the lowest possible number. So if we could number it left to right, that would put the hydroxyl group at number 5. But if we number it right to left, that puts it at 2. Since 2 is less than 5, we're going to number it right to left. So now we know that the hydroxyl group is on the second carbon. So this becomes 2-hexanol. Finally, we need to look for the other substituents. In this case, we have a methyl, and now it's on carbon 5. So we just add that to the beginning, just like what we did before with our alkanes. So it becomes 5-methyl 2-hexanol. That's how we name this alcohol compound. Okay, so why don't you go ahead and give it a try. Give the IUPAC name for the following compounds. This is phenol down here. We talked about that at the end of last chapter. So if you need a brush up on that, you can check out the end of the sample exercise packet from the last chapter. If not, of course, read through the book, and we'll look at the answers here in just a minute. So go ahead, pause the video, try to name these compounds, and then we'll do it together when we come back. Okay, all right. So I'll assume that you paused the video and you named it, gave it a shot. Now let's go ahead and try to do it together. So rather than walking through the book here, let's do it together this way. Now, here's our OH group, right? So we have to pick the longest carbon chain that contains the OH group. So it looks like it's this 1, 2, 3, 4, 5. I could go 5 up here as well, but no need to necessarily do that. So that would be pentane, right? But I see that we have, excuse me, so sorry for that. I see that we have an alcohol here, so we know it's not pentane, it's pentanol. Furthermore, I can see that the alcohol is on the second carbon, so we're going to call it 2-pentanol. Finally, looking for any other substituents, I see there's a methyl group on the 4th carbon, so that's 4-methyl 2-pentanol. And that's how you can kind of walk it through there. Now down here, we should recognize, okay, we have a hydroxyl group on a benzene ring, that's phenol. So that's where we start from. And then with phenol, we're always going to number it so that the carbon that's bonded to the hydroxyl group is carbon number 1. So to number the substituent, the bromo substituent here, we have to go carbon 1, 2, 3. So it should be 3-bromophenol. And that's how we name that. Okay, so let's go ahead and look at the books, how the book does it here. So yeah, right, so we have a pentanol and we have a phenol. This is 2-pentanol because we number it this way. This has to be 3-bromophenol and 4-methyl 2-pentanol. Okay, so that's for alcohols. Now we'll talk briefly about how this links to health, because of course it has a very strong link to health. The main type of alcohol that we commonly refer to just as alcohol is ethanol. And ethanol is, what can you say? It's an intoxicating chemical that has been known and has been used for humans since prehistoric times. Like we've excavated, archaeologists and archaeologists have excavated breweries and vineyards and fermentation jugs from many thousands of years ago. So it's been with us for a long, long time. And the reason for that is that it basically is the result of if you have grains or any other type of sugar, so like grains like how you use different grains with beer, for example, or if you have sugars from grape juice, for example, and you let yeast grow in it, yeast will turn that sugar, glucose, into ethanol and carbon dioxide. Carbon dioxide is left as a gas. This is a liquid that sticks around. Okay, now for industrial purposes, if you need really high purity ethanol, it's harder to get it from a fermentation process. And it's much cheaper to use ethane, which is kind of a byproduct of a lot of other industrial processes that involve fossil fuels. And you can just hydrate it using water to produce ethyl alcohol. And then this is a high purity solvent for things that you're not going to drink, for example, like perfumes and varnishes, and rarely some medicines. Okay, so next up we have glycerol. Glycerol you probably heard of because it is a skin softener. So if you look at the back of your skin lotion or other cosmetic jar, you'll see in the ingredients list, usually there's some type of glycerol or modified glycerol. And what it is it's propane, so 1, 2, 3 carbon chain, where each of those carbons has a hydroxyl group on it. So it's kind of like a tri-alcohol. It's a trihydroxy alcohol, as we would say. And you can get it actually from oils and fats when you produce soaps. So it's relatively cheap and expensive. Okay, next up, we have ethylene glycol, which if you've ever lived in a place where it gets to freezing temperatures in winter, you know that your car needs to have a coolant system that doesn't freeze at 32 Fahrenheit or 0 degrees Celsius. So ethylene glycol is often used as an antifreeze in various heating and cooling systems, especially in your car. It can also be used as a solvent for different paints and inks. And yeah, I guess Dacron can also be produced from it. I'm not totally sure what that is. Now, ethylene glycol unfortunately tastes very sweet, so it can be really dangerous if it's stored around pets or children. If you do ingest it, it forms insoluble salts in the kidneys and it can break your kidneys. So if you have any of this around house, you have to make sure that it's very safely stored away from children and pets. Okay, next up, bisphenol A. So BPA is a type of plastic that's used, and you can see here we've got a phenol group here, right? There's 2 separate phenols groups that are kind of both on like a propyl chain here in the middle. And this is basically what we call a plasticizer. It makes the plastic easier to work with. And it's used to make polycarbonate, which is often used to make beverage bottles and baby bottles. However, when you wash polycarbonate bottles, some of this BPA will actually leach out. And then that BPA can basically interact with your body. So there's still a lot of research going on with this, but for now, it seems like the research is showing that this BPA has some toxic effects, whether it's mimicking certain hormones that can mess up your personal homeostasis. That seems to be the case. So that's why you see BPA free as like a common thing. And pretty soon, I think there's supposed to be some rulings on this from the regulatory agencies to kind of get rid of using bisphenol A in plasticizing anything that's used for consumption. Okay, and then finally, phenols also are responsible for a lot of the big odors of herbs that we use. So phenolin, for example, is a phenol compound. That's of course vanilla, the essence of vanilla. Eugenol is from cloves. Thymol, of course, from thyme. And isoeugenol is from nutmeg. So those very fragrant spices, a lot of their compounds, the reason that they smell so good is the phenols that are in them. Okay, so going from things that smell really good to things that smell really bad. We've got phenols that smell pretty good sometimes, and then thiols that smell awful. So you're familiar with thiols because these thiol odors are found in cheese, onions, garlic, and oysters. So those aren't bad, right? That's not too bad. But of course, skunk spray as well is this one, trans-2-butene-1-thiol. If you've ever smelled a skunk, you'll never forget it, obviously, because it's extremely I don't even know how to describe it, like burning rubber. Very disagreeable, as your book says. And what else? Oh, what else was it? Rotting eggs as well. Rotting eggs as well have a thiol smell that kind of really, again, really hits you in the wrong spot in your nose. Now, the good news is we are set up, we've evolved to detect thiols to a very small degree. In other words, our noses are really good at detecting thiols. So we can use that, for example, with gas leaks. While like natural gas, if it were to leak, you can't smell it. Now that's dangerous because natural gas leaks, that means that the air around you is explosive. So that's no good. So what we do is we dope it with a little bit of methane thiol, and methane thiol you detect in your nose at a very, very low concentration. So you smell the methane thiol and you know, hey, there's a gas leak. I got to go turn off the stove. Okay, now how do you name thiols? Well, it's actually not too bad. For the IUPAC system, what you do is you just basically add thiol to the end of the alkane chain. And again, you just number the longest carbon chain, numbering it from the end that's nearest to the SH group, right? So methanol, that's CH3OH. The thiol equivalent is CH3SH. We just call that methane thiol. Ethanol becomes ethane thiol. And here, for example, is 2-butane thiol, where the thiol group, the SH group, is on the second carbon of a butane chain. And yeah, so I guess this is some of the ones here that we can see. So methane thiol comes from oysters and cheese. You can smell it there. Propane thiol is from onions, and then 2-propene-1-thiol is from garlic. So it's not all bad. Not all bad smells, right? Onions smell good. Garlic smells good. Cheese can smell good. Yeah. Okay. Finally, we've got ethers for the first part of this chapter. I know we have aldehydes and ketones in the second half, but I think this is the last part of this lecture that we have a new compound for. So ethers contain an oxygen that's between two carbon groups. And those carbon groups can either be alkyl groups, like methyl group or ethyl group, or they could be aromatic rings. Now, because there is an oxygen in the middle, this oxygen is going to have two bonds, right? So carbon has 4 bonds, hydrogen has 1 bond, and oxygen is going to have 2 bonds, just like in water. So because of that, this oxygen has 2 lone pairs in its Lewis structure. And because of that, that means it's got a bent structure. Now that gives some amount of polarity to these ethers, even if it's not as polar as an alcohol. Okay, so the only type of nomenclature you need to know for ethers is the common name. The IUPAC name is a little complicated and it doesn't really come up too much. So the way that we do this is we name the two, we think about it this way, basically. Think about the oxygen here as the ether, okay? And then we name the carbon groups that are coming off of it as substituents of it. So here it's CH3O, CH2, CH2, CH3. So we split it up. We say, okay, there's a CH3 group over here. That's a methyl group. Over here, it's CH2, CH2, CH3. That's a propyl group. So we just take those together and say methyl, propyl, ether. That's how we name it in a common way. And again, we're only going to use common names for now. It's a little more complicated otherwise. Okay, now what are ethers good for? Well, ethers famously are really good at knocking people out. And this was their first application in the early 1900s. Diethyl ether was one of the first compounds that was used as a general anesthetic. In other words, that's something that makes you go unconscious. So, for example, you could undergo surgery, or if you were in a lot of pain, you'd be relieved from pain. while you were unconscious, and the doctor could operate on it. Yeah, so anesthesia, this is something that you'll probably experience in the medical field. Sometimes patients need anesthesia for various operations. A general anesthetic is something that blocks signals to the awareness centers of the brain. And during that time, the patient will have a loss of memory, won't feel any pain, and it will have an artificial sleep. Yeah, now, so the ether is really good, but it is somewhat toxic. Basically, it gets processed into alcohol, and that alcohol can then be really strong. There used to be a movement for ether cocktails, where basically like you drink a little bit of diethyl ether, and your body processes that into twice the amount of alcohol that you would have had, and it hits harder because it's processed in your body rather than going through your stomach. So very dangerous, very bad hangovers is what people say. So don't do that at home, but I'm just saying that is what people have done in the past. So a new range of anesthetics were developed that are ethers as well, but they replace the hydrogen atoms with halogens, and that basically reduces the flammability of the ether. So these are more like liquids or vapors at room temperature, and you don't have the same storage problems. So there's fullerene, ethane, suprane, sevoflurane. You're not expected to memorize any of these, but you may recognize some of the names if you've already been practicing in the clinic or been working in a hospital. Okay, so why don't you go ahead and give it a try with sample exercise number 2. Give me the structures for the following compounds. We've got 3-pentanol, we've got ethanol, and diethyl ether. So go ahead, pause the video, and when you come back, we're going to take a look at the structures. So give it a pause. I'm going to take a sip of tea. Okay, we're back. Let's go ahead and draw the structures of the followings. Now, I'll do it with you here because I think it's better if I show you how I think it through rather than what the book does. So 3-pentanol. Pentane is a 5-membered or 5-chained carbon, right? So that means we've got 1, 2, 3, 4, 5 carbons. 3-pentanol tells me that the alcohol group, the OH group, is on the 3rd carbon. So 1, 2, 3, OH. Not too bad, right? Okay, how about ethanol? Okay, ethanol is 1, 2 carbons long, and then it's got an OH group on it. Hey, that's not too bad, right? And finally, diethyl ether. So ether, we know that's an oxygen, right? And then it says diethyl. So there's 2 ethyl groups coming off of this oxygen. So ethyl group 1, ethyl group 2. Diethyl ether. Okay, let's walk it through this way. Yeah, you can just see kind of the same thing. This is the condensed structural formula if you prefer drawing those. I, of course, prefer drawing the line angle structures because they're just a little quicker. Okay, next up, let's talk about some of the properties of alcohols and the reactions that they can do. Okay, so alcohols will be classified by a numbering scheme. We call it primary, secondary, or tertiary. Okay, and the way that we're going to classify it is we're going to look at the carbon that is attached to the OH group. Okay, and then we're going to ask ourselves, how many carbons is that carbon attached to? So in ethanol's case, the hydroxyl group is attached to a carbon. That carbon is attached to one other carbon. If the carbon is attached to one other carbon, we call that a primary alcohol. Okay, next up for 2-propanol or isopropanol. The carbon that the OH group is attached to here is now bonded to 1, 2 other carbons. This is what we call a secondary alcohol. So isopropanol is a secondary alcohol. Then finally, we have a compound terbutanol here. The OH group is bonded to a carbon that's bonded to 1, 2, 3 other groups. That is so 3 other carbons, that is going to be a tertiary alcohol. So this is just a quick way that we can classify alcohols, and that can tell us a little bit about the reactivity of those alcohols. Okay, so why don't you get some practice on classifying here with A, B, and C. Again, ask yourself, how many carbons is the carbon that's bonded to the alcohol group bonded to? And then is it primary, secondary, or tertiary? Go ahead, pause the video. You can review the previous slide if that helps. And when I come back, let's go ahead and look at the answer. So pause. Okay, we're back. So for the first one here, the OH group is bonded to this carbon. This carbon is bonded to 1, 2 other carbons, so that's secondary. How about this one? This OH group is bonded to this carbon, which is only bonded to 1 other carbon, so that's a primary alcohol. C, we have this OH group bonded to this carbon, which is bonded to 1, 2, 3 other carbons. 3 is tertiary. So we have secondary, then primary, and tertiary. All right. Now, one of the key parts of alcohols is that they tend to be soluble in water, at least if you don't have too long of a nonpolar chain. So here is kind of like where polarity enters the mix. The OH group itself is very polar because the oxygen is bonded to a hydrogen. Oxygen is much more electronegative than hydrogen, just like in water. So that causes a dipole where the oxygen is partially negatively charged, the hydrogen is partially positively charged. So that's a polar group. Now, at the same time, we have these carbon chains, which are just chains of carbon-carbon bonds, which are nonpolar, and carbon-hydrogen bonds, which are nonpolar. So this organic section of the molecule here, that tends to be nonpolar. So there's kind of a balance here. The longer that the tail of the alcohol gets, the less soluble in water it is. So when you compare ethanol, which is fully miscible with water, that means that you can have 1% ethanol in water, or you could have 99% ethanol in water, and every percentage in between, all mixed together fully as a solution. And down here we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So this is octanol, 1 octanol. Here, because of the length of this nonpolar chain, that means that it's going to be insoluble in water. The water doesn't want to interact with this nonpolar tail. Okay, so here's the deal. So alcohols that have 1 to 3 carbons are going to be soluble in water. And then as you increase that, 4, 5, and 6, they get less and less soluble. So that's where we're going to put the line is at number 4. So butanol, 1 butanol is slightly soluble in water, and then 1 pentanol is insoluble in water. So 1 butanol is right on the line. Basically, like if you add enough 1 butanol, it'll separate out from the water, but a little bit of 1 butanol will go into water if you have enough water. Okay, so now linking it to hand sanitizers. We're all very familiar with hand sanitizers by now, I'm sure. There's man, what a strange couple of years it's been. It used to be hand sanitizers were mostly made with isopropyl alcohol, but hand sanitizers, when they became extremely popular or widely used during the COVID-19 pandemic, there were shortages, and more and more of them were made with ethanol as the active ingredient. So these are really good at killing bacteria and viruses because alcohols, because they have that non-polar tail and the polar head of the OH group, they can disrupt the cell membranes and then the viral capsid shell, protein shell. Basically, those dissolve in water, or I'm sorry, they dissolve in ethanol and alcohols is the way that you can think about it. So usually they're between 60% and 85% volume over volume, alcohol to water. And they tend to be very flammable. Now, you don't want to actually burn them. I don't know if anyone's played around with them at all, but they produce a transparent blue flame that can sometimes be invisible. And that can be very dangerous because if it's invisible, you can't see it, but it's a fire. So yeah, which is a real problem. Okay, and then finally, we'll just point out your triclosan. So this can accumulate in the environment, promoting growth of antibiotic-resistant bacteria. So this was a big thing with my my high school biology teacher. He always said, never buy antibacterial soap because soap itself is antibacterial. Just having soap, or in this case, like we're talking about ethanol and propanol, those do enough to destroy whatever bacteria is on your hands. You don't need to add more antibiotic stuff to it. And the same thing goes for the soap and for the hand sanitizer. The more of this that's out there, so triclosan is an antibiotic. In other words, bacteria will take it up and that'll kill them eventually. The problem with antibiotics is that as a toxin to the bacteria can evolve to live with it, basically. Like over enough generations of bacteria, eventually one will find the right way to process it or get rid of the triclosan in a healthy way, and then it can spread unchecked. This is a big problem in hospitals where bacteria are getting resistant to a lot of the antibiotics that we use commonly for a lot of different reasons. So basically, like new antibiotics need to be discovered to destroy these, and just the rate of antibiotic discovery is very slow, and the rate of evolution of bacteria is relatively fast. They're beating our antibiotic molecules before we can discover new ones. So this is like the MRSA. It's the boy, I forgot what the first one is, but it's the resistant staph infection. So antibiotic resistant staph infections are really problems at hospitals right now. And you don't want to be anywhere around that, because you getting it means that we don't really have like ways to treat it. And then even a very minor infection can become a real problem because we just don't have the tools to fight that antibiotic resistant infection. So long story short, don't buy the extra antibiotic soap, just use normal hand soap. Okay, so finally, phenols. Now, phenols are also slightly soluble in water. And the reason for that is that this OH group basically acts as a weak acid, and it produces this phenoxide ion. So it acts as a weak acid, like we said, so it donates a proton, water accepts a proton acting as a base, and it forms this phenoxide ion. Now, it is toxic, and so it was used as an antiseptic, but it's also toxic to us, so we don't really use it as an antiseptic anymore. Okay, so let's look at sample exercise number 4. Tell me whether or not each of these is soluble in water, and tell me why. So pause the video here, take a look at these two alcohols, figure out which one's soluble, which one's insoluble, and explain why. Pause the video, and we'll be right back. Okay, so let's take a look here. Well, let's count up the number of carbons on the chain. Let's start down here. 1, 2 carbons, that's ethanol, that's soluble in water. It has fewer than 4 is the way you can think about it. Then we up here have 1, 2, 3, 4, 5, 6 carbons in a chain. That's more than 4 carbons. That means it's going to be insoluble in water because it's got a long non-polar chain. Oh, wow. Okay, so that covers it for this lecture. We're about halfway through the chapter 12 now. In the next lecture, we're going to talk about aldehydes and ketones and some of the reactions that they go through. But until then, I'll see you soon, and let me know if you have in the comments if you have any questions. Bye-bye.